All right, everyone. So even though we have already watched a video, or in class we've done part 1 about limiting an excess reactant as a concept, we all know that this unit is all about stoichiometry and those T-charts. So I want to show you how limiting an excess reactant can affect your calculations for your theoretical yield. So one thing we're going to need to do is first balance this equation. So keep in mind we have, I'm going to do it above it, so we have aluminum, copper, and I'm going to keep sulfate together. So if we look on the reactant side, we have 1, 1, and 1 of each of those, and on the product side we have 2 aluminums and 3 sulfates and 1 copper. So to balance this out, if we balance aluminum first, we'll need 2 here, and that will give us 2 aluminums on the reactant to balance. To balance our sulfates, we're going to need a 3 here to have 3 sulfates, and that also gives us 3 coppers. So we'll need 3 coppers on the product side to balance out, and that means the coefficient for aluminum sulfate is just 1. So once you have a balanced chemical equation, you know, we have our mole ratio and everything that we need. And so what happens is, let's say we're doing this experiment in class with aluminum and copper sulfate, and we have 100 grams of each reactant to start with. They want to know how much copper could be formed. So copper is one of our products, but because the mole ratios are different and the molar masses are different, starting off with 100 grams of each doesn't mean that you will be able to produce the same amount of copper based on those 2 reactants. So what you're going to have to do is actually determine which one, or how much copper could be produced from 100 grams of aluminum and how many grams of copper could be produced from 100 grams of copper sulfate. So that is 2 3-step problems. So what we're going to need is we're going to need the molar masses of a couple of things. So let's go ahead and do that. So we need the molar mass of aluminum, which we know is going to be 26.98 grams. We need the molar mass of copper sulfate, which has 1 copper and 1 sulfur and 4 oxygens. So copper is 63.55, sulfur is 32.07, oxygen is 16. Sorry that I'm writing this so small, but I want to save our space for the real work of the T-charts. So if we add this together, 16 times 4, when we add it all together, we get 159.62 grams, okay? And then the molar mass of just copper is 63.55 grams now of copper. Now we don't need the molar mass of aluminum sulfate because it's a product, but it's not the product we are looking at. We are staying focused right here on just plain copper, okay? So that means we also need to pay attention to our mole ratios. So we know that the mole ratio for aluminum to copper would be 2 to 3, and copper sulfate to copper is 3 to 3. So we'll use both of those. So we start off with 100 grams of aluminum, and we start off with 100 grams of copper sulfate. So we will actually have 2 T-charts going. Now, the end of them will be identical because we're ending in the same product, but the beginning is different. So remember, whatever reactant or whatever unit and chemical we have here has to show up at the bottom. That pattern is true no matter what your T-chart is. So if we have grams of aluminum and grams of copper sulfate at the bottom, that means we need to use their molar masses. So our molar mass of aluminum is 26.98, and it's always with 1 mole of the same chemical above it. And for copper sulfate, it was 159.62 grams, and again, 1 mole of copper sulfate above it. But that is not what we want to know. We want to know the mass of copper. So now we need to, now that we're in moles, we can use our mole ratio, okay, because, oops, sorry about that. We are going to use our mole ratio because we're going to need moles of aluminum at the bottom and moles of copper sulfate at the bottom. So we know that our moles of aluminum is 2 and our moles of copper sulfate is 3. And where they both have in common is our 3 moles of copper will be at the top. Okay, and this is where things become identical because they will both end. We want the mass of copper, so we know that 1 mole of copper is 63.55 grams of copper. And so that part of our T-chart will be identical. So now that we have grams of copper of everything, our units cancel out, all of that, we can put this into our calculator. Remember, we multiply by what's on the top, we divide by what's on the bottom, and for aluminum, that will give us 353.3 grams of copper. And for the copper sulfate, it will give us 39.81 grams of copper. So what we see here is a couple of things. If I have 100 grams of copper sulfate, this is the maximum amount of copper I can produce with that amount of my reactant. If I have 100 grams of aluminum, the maximum amount I can produce is 353.3 grams of copper, okay? So these would be our theoretical yields. However, if I have both of these at the same time, one of them is going to limit the amount, and that would be the lowest. Since this is the lowest amount, then this is our theoretical yield. Now, if I had a lot more copper sulfate, then I could maybe produce more copper. But since this amount of copper sulfate can only produce about 40 grams of copper, that means I cannot produce up to 350 grams of copper the way my first reactant can. So when we think about what's limiting and what's excess, our limiting reactant is the copper sulfate because it produces the smallest amount, whereas our excess reactant would have to be the aluminum, okay, because it can produce a lot more copper, but it's being limited and held back by the copper sulfate. So aluminum will be in excess. We will have a lot of aluminum left over. Now, the question then becomes, okay, well, how much of our excess reactant was left over? Well, we know we started with 100 grams. So what we do is we say, okay, well, if this amount here is my actual theoretical yield, the amount of copper I actually used, you can work backwards to aluminum to find out how much was actually used up. So if we have 39.81 grams of copper, we can work backwards to figure out how many grams of aluminum were actually used in the experiment. So we have 63.55 grams of copper is what 1 mole of copper is, and the ratio between copper to aluminum is 3 moles of copper for every 2 moles of aluminum, and we know that 1 mole of aluminum is 26.98 grams of aluminum. And so I'm pretty much doing that first T-chart, but in reverse, and starting with the amount that I actually was able to use and create. And so when we put this into our calculator, we see, okay, we only used 11.27 grams of aluminum. So that means if I want to know how much was left over, then we would say, okay, we had 100 grams of aluminum. We used 11.27 grams of it. And so that means 100 minus 11.27 will give us 88.73 grams of aluminum left over. Okay, so this is going to be really important. You're going to have a problem like this on your test. I can guarantee it. It's my bwahaha kind of mean thing. But honestly, at this point, your T-charts should be second nature to you, okay? I hope that you have done enough practice that doing the T-charts is completely fine and you're pretty quick at them. And that really this just becomes, okay, understanding our concepts of limiting an excess reactant. Now, you do have some practice here, so I've given you an example problem to do. I highly recommend that you balance this equation and do your practice, because I can guarantee that you will have a question like this on your test. So, and if I went too fast for you, rewatch the video, pause me, slow me down, put my speed at half speed or something, and enjoy.